Swayam Prabha. Digital India. Educated India.
So, we will continue in this class with the analysis of 1D proton spectrum. We looked at some 5 examples of how given a spectrum and only the molecular composition we can try to figure out the possible structure which fits the spectrum. Of course, if more data is available to us like IR and carbon spectrum, it will be useful, but in absence of that also we can get a fair idea of what the structure could be. So, we will continue with that in this class. So, let us start from this example number 6. So, here this is the molecular formula or the composition given to us. So, there are 14 hydrogens and 2 oxygens, 7 carbons, and this is the spectrum. So, if you look at now this relative intensity, it is very interesting that it is basically giving a fractional integral, and this is essentially there are triplet, a singlet and a quadret. Now, the question is how do you interpret this integral which is fractional. So, remember again as we saw in the last class, in NMR all you get is what is called relative integration. Unless you take a reference and then compute, calculate, quantify, you will get the absolute value, but if you look at only within this spectra, within this molecule, it is only a relative value which you will get. So, then one has to take a judgment on how to analyze this. So, but I expect let us say 14 protons, okay. But if you add up this 4.5 plus 1.5 plus 1, it adds up to 7. So, what it means is if I want to get 14, I have to multiply all of this with 2. So, if I multiply by 2, I will get 2 here, 9 here and 3 here. So, that means there are 3 protons in this, 9 protons in this tall peak, and there are 2 protons in this. So, that is how we have to basically interpret. So, now if you look at it further, now what is happening is we do not see any peak downfield shifted around 4-5 ppm. What it means is that I do not have any hydrogen. See, remember if in the previous class and slides we saw that if a hydrogen is attached to a carbon which is attached to oxygen directly, OCH kind of a system, then that H comes somewhere between 4 and 5, but that is not what we see here. All of them are in this upfield shifted. So, that means there is no OCH in this particular case. So, these 9 protons has to be basically 3 methyl protons, because CH3, CH3, CH3 only then you get 9, and it looks like that all these 9 protons are chemically equivalent. Therefore, they are all coming at the same place, they are equal, same chemical shift value, and they are actually 9 peaks, because 3 into 3 is 9, and they seem to be singlet, which means they are not coupled to any hydrogens. So, if they were coupled to any other hydrogen, you would expect to see multiplets like this, but because there is a singlet, it means this is a 3 CH3s which are kind of isolated, means they are not coupled to any hydrogen. So, what is that which comes to our mind which will satisfy this particular condition, and that is basically like this. It could be a C which is attached to 3 methyls, and therefore, none of these methyls are therefore coupled to any protons. So, if you look at this particular case, you can see here that these 3 hydrogens are isolated, because this C does not have any hydrogen. The nearest hydrogen could be somewhere here, but that is very far away. So, therefore, these 3 hydrogens, these 3 methyls are chemically equivalent, okay, and they are not coupled to any hydrogen. So, you expected to get a singlet which is corresponding to 9. 9 why 9, because we have multiplied this by 2 now to get 2 is to 9 is to 3. So, this is one particular answer, one answer for this origin of this peak. Now, we have seen a quadret and a triplet. Okay. So, typically if you multiply this by 2 you get 3. So, what is basically has happened, we have rescaled this integral. So, we have rescaled this, we call it 2 9 3. So, now what it means is whenever you see 3, it basically means it is a CH3 and this is a CH2 because 2 hydrogens. Now, this CH3 if it is coupled to this CH2, so suppose let us say I have this kind of a moiety, then in that case what will happen is that this CH2 is now coupled to this CH3. So, these 2 protons we will expect to get a quadret, and that is what is here. And similarly this CH3, when it is coupled to a 2 proton, you expect to get a triplet, and that is what is this peak. So, you see whenever you see a triplet and a quadret, you typically expect that to be this particular system. And because this is coming in this zone between 0 to 2.5, therefore, it is not directly attached, there is no oxygen here, direct oxygen, okay. But there is definitely a electronegative system, because this CH2 seems to be downfield shifted around 2.5. Normally this CH2 comes around 2 ppm, but because of something here, that is showing up at 2.5. So, what that could be? That could be a carbonyl. So, if you have a carbonyl group, and that carbonyl group will basically give you, because of that this CH2 will get shifted and it will come at downfield system. So, we get a carbonyl and a CH2 CH3 moiety on one side, and there is this one also present in the molecule. So, now if you join these together, this is the structure what you would expect. You would expect this particular structure where there is a 3 CH3s attached to this carbon, and this oxygen is this carbon is attached to this oxygen, and then this carbonyl CH2 CH3 is present. So, this is what we discussed, that this CH2, remember this carbonyl, you could say why do not we flip it to the other side, that means this O comes this side, but then if that is so, then this OCH2 would have come somewhere at 4 to 5 ppm, but that is not what we are seeing here. Therefore, this oxygen is on this side and not on the other side, and therefore, this is what we get. So, now if you had a carbon spectrum again, you could have figured out, because you would have seen a quaternary, this is a quaternary carbon, and that would have got downfield shifted because of direct attaching to oxygen. But even without that, we can see that we can fit the structure to this spectrum. So, this is an example. Let us look at the next one, where now we have an halogen in addition to 2 oxygens. So, now here what is interesting is we are seeing a very downfield shifted peak and that the integral for that is 1. So, what it means? It means this is an carboxylate, the acid proton COOH. Again, this you have to refer to the slide where we saw that carboxylate protons and aldehyde protons come very downfield shifted. Typically the carboxylate protons come around 10 to 11, and that is what basically you are seeing here. You are seeing that there is a carboxylate proton here, that is 1 proton, and then there is these are 2 each, and that corresponds to 5, and that is what we are seeing 5 here. So, now you can see there is an 4 here, that means there is an attachment to a OCH group is present. Only if there is a OCH group, remember we expect to see a peak somewhere between 4 to 5 ppm. So, there is an OCH group, but then the next one there is a chlorine, and that also is an electronegative atom. So, therefore, there is a hydrogen which is attached to a chlorine, and that is also getting downfield shifted. So, what could be the structure which will satisfy this particular case? So, this could be like this. So, we probably have acid group. So, let us build the structure probable. So, this is as an acid group, and this has a CH2, and there are 2 CH2s because both are proton, they both are 2 hydrogens, but one is attached to oxygen, and therefore, it comes downfield shifted, and one probably is attached to Cl, and it comes here. So, if you look at this, but there are 2 oxygens here, there are 2 hydrogens, but so that cannot be, this possibility is ruled out because we already have taken care of these 2 hydrogens. So, then what could be the structure which will satisfy this? This will basically has to be something like a branched chain situation where we have this one. So, let me draw this again. On this particular case, so basically there is a COOH, and there should be one CH2, and then there should be another CH2 attached to Cl. So, if you have this kind of a situation, then this particular molecule, now this particular CH2 will be triplet because of this hydrogen, and this CH2 will be triplet because of this hydrogen, and this one will be downfield shifted because of this, and this also is downfield shifted because of this. So, if this is the case, yes. So, this is the structure of the molecule what we see, this is the answer, and we see this matches with the spectrum. So, this CH2 which is attached to Cl is basically downfield shifted here coming at this position, and that CH2 which is attached to COOH is coming at 3 ppm, because there is no oxygen. Remember again, if you look at the slide we looked at, if you have a CH2 Cl or C attached to oxygen or halogen or C attached to nitrogen, then you expect a downfield shift of this proton, but here it is attached to oxygen, it is attached to carbonyl, not directly to the oxygen, and carbonyl shifts not so much as downfield as you expect from Cl. So, this is what is the structure matching with this spectrum. Okay. So, the main important point is that a peak is observed which corresponds to a carboxylate group. So, let us look at the next example. Again here this seems to be the same molecular formula as we saw in the previous slide. So, that means it is a structural isomer of the compound. So, in NMR the structural isomer can be distinguished by looking at the J multiplet pattern, which if you use IR spectroscopy kind of difficult to figure out whether there is a branch chain, because as far as the functional groups are concerned, if they are same, IR spectroscopy cannot distinguish so much. Similarly, if you look at mass spec of course will give you the same mass for both the systems. So, a regular mass spectrum will not be able to help in deciding whether it is isomer or not. So, NMR is that way a unique nice technique where you can differentiate two structural isomers from each other. So, let us now look at this example. So, again here we have a carboxylic acid group, that is why proton is single proton and coming very much downfield shifted. Now, there is here instead of two triplets what we saw, there is now a quartet and a doublet. So, again remember this is CH3. So, what it means? It means it is a methyl group, CH3 methyl group, and that is seems to be coupled to one hydrogen, because only then you get a doublet. Okay. And that one hydrogen is coupled in turn to this 3. Remember, if A is coupled to B, B is also coupled to A. So, one proton is coupled to another proton, that proton is also coupled to this. So, if one proton is coupled to a methyl group, n plus 1 rule means you should get a quartet, and that is what you see. Okay. And look at the chemical shift value, it is coming between 4 and 5. So, that means it could be directly attached to oxygen or it is attached to a halogen CCl or CC. Remember halogen CCl or CO or CN all have downfield shifted values. So, most likely if you now put all this together, before we see the final answer, let us try to work out what could be the structure. So, basically now this says that I expect a CH3 here, that is why I get a 3 peaks, 3 integral, but this is doublet. So, that means it is attached to CH, only one hydrogen. Okay. And this CH is now coming downfield shifted, therefore, it should be attached to a oxygen or a chlorine, which is what we expect from the molecule. And further this is probably an acidic group here, because only then you can explain that there is a COOH peak coming at 10 ppm. So, let us see whether that is the correct answer, and if you see the structure, this is what we see, this is exactly what is shown here. So, you can see that this CH is now a doublet quartet, because it is coupled to 3 hydrogens, that is what we saw here, and this CH3 is coupled to only 1. So, this CH3 is a doublet, and because of this attachment to a chlorine it is downfield shifted. Not only that, it is this hydrogen is also attached to this carbon, which is attached to carbonyl, CO double bond O and another O. So, therefore, this CH, this particular hydrogen is downfield shifted because of 2 electronegative groups, one is the chlorine and other is this carboxylate group. And if you see, look at this here, even it is also downfield shifted. Remember again, methyl peaks are between 0 to 2, and if it is at the edge of this, that is around 2 ppm, what it means, it is kind of a methoxy group, or it could be not a methoxy, sorry, it could be a CH3 attached to a carbonyl, or it could be a CH3 attached to some more electronegative atom. But what is happening is, this is because of this chlorine, there is electronegative inductive effect. So, if you recollect the inductive effect, even though the CH3 is not directly attached to chlorine, there is a separation by 2 bonds, and that also is enough to create a little bit de-shielding of these hydrogens, and that is what is causing this thing to come downfield shifted. So, taken together we can see that this structural formula, this satisfies our spectrum. So, now in the next two examples we will look at aromatic groups. So, we are till now not analyzed the aromatic systems, these are all been aliphatic with different functional groups. Now, let us see what happens in the case of aromatic. So, there are different ways to figure out if, so this is the molecular formula which we are going to look at the composition. Now, first thing is, how do you know there is an aromatic ring here? Remember, in chemistry there are rules which can tell you whether there is an aromatic system. We use what is known as index of hydrogen deficiency. So, that we will not go into in this course, or you can use what is called rule of 13. These are the rules which typically chemists will use to figure out the number of pi bonds, that is unsaturation, the degree of unsaturation and so on. So, that is one way to find out if there is a aromatic benzene ring present. Another way is from NMR you can look at this spectrum here. What will happen is you will get a little complicated peaks pattern somewhere between 7 to 8 ppm. So, this, remember we saw that this belongs to aromatic amino acid aromatic groups, functional groups, but you may also get amides here, but here we do not see any nitrogen and oxygen. So, that means there is no amide possibility. So, typically if you see a bunch of peaks, remember the word bunch of peaks coming clustering around 7 to 8 ppm, immediately it denotes, signifies a presence of an aromatic ring. So, what we do normally is we do not analyze the aromatic pattern. The reason being that aromatic pattern, there are two things. One is there is a coupling, long range coupling present. So, the hydrogens are not only coupled to the 3 bond hydrogens, which is what typically we use when we analyze this type of data, but it is also coupled to a longer 5 bonds away and so on. And there is, these are strong coupling, in the sense the chemical shift difference between them is very small and the coupling is bigger than that. So, we have what is called a strong coupling scenario, and therefore, because of that the peak pattern what you see here in aromatic ring is not straightforward to interpret compared to what you see here. So, therefore, what typically we do is we bunch all the aromatics together and then get a common integral value for that, and also the presence of peaks, and this already tells us there is an aromatic system, plus the integral under this together will give me the total integration value relative, and that is tells me that there are 5 protons. So, essentially it means there is a phenyl ring, the benzene, the phenyl group, and that is why there are 5 hydrogens. So, that is what we interpret, how we interpret this side. And now coming back to here, this is again the standard interpretation what we have been doing. So, what we have here is a triplet, a doublet, and here it is a quintet, and there is a sextet. Now, sextet is 6 protons. So, 6 protons can be 5 protons, 5 protons will give you a sextet. So, what it means, again remember, a sextet can possibly come, if you have a CH which is sandwiched between CH2 and a CH3, because only then this hydrogen is coupled to this and this 5. So, 5 plus 1, 6 peaks. So, that is what you would expect for a sextet. Okay. So, we will see, this is how we can think about. And then if you look at this methyl, there are 2 methyl groups here. Again remember, always between 0 to 2 typically the methyls will come, and therefore, now the methyl is, remember there is no oxygen here. So, there is no electronegative atom here. So, that is why you do not see any peak in this 4 to 5 ppm. Okay. So, therefore, this is all coming in this side. So, these are all purely aliphatic spin systems, aliphatic protons, and here you can see there is a triplet here, that is a methyl, which that means is attached to a CH2. Only if a methyl is attached to CH2 you expect the methyl to be a triplet. So, that means this could be particularly, if you think about it, this could probably a CH3 attached to a CH2. If that is so, this will give 2 plus 1 equal to 3 peaks, and this particular hydrogen is coupled to 3. So, 3 plus 1, this will be quartet, and this will be a triplet. So, you see that is how we can think about it, and therefore, this quartet and triplet which we are expecting could be this quartet, sorry, this is a quintet here. So, there is no quartet. So, that means this particular possibility is not there. So, there is a CH3 which is attached to CH2, but the CH2 is now attached to some other hydrogen, and that hydrogen is probably, so that means this particular peak, this particular carbon is attached to a CH. So, then 1 plus 3 4, so this is 4 plus 1 quintet, and that could be probably this quintet here. So, what we are seeing. Okay. So, that could be the quintet here. So, we have basically a spin system like this CH3, CH2, CH. Now, remember we drew here CH, CH3, CH2. So, that means this CH could be part of this CH2, CH, CH3. Okay. And then where do we fit the aromatic ring? Then aromatic ring probably is coming basically from attached to this CH2, because that is the only where valency is left. Okay. Because if I put a phenyl ring here, then I can have phenyl ring, a CH2, a CH, CH3, and to this CH here is attached a CH2, CH3. So, if you put this structure all together, this is what you get. So, you see this CH is attached. So, basically this proton is getting me a quintet. So, basically it has this CH. So, it is attached to CH2, CH3, what we saw, okay. But this CH2 is attached to a CH3. So, therefore, this CH2 is basically this here, what we saw here, that this CH2 is having 3 and 1 4. So, 4 plus 1 5. So, 5 means quintet. So, this CH2 is this quintet here, okay. This is this mapping, and this CH3 is expected to show a triplet because of these two, and this CH3 is this CH3 here, and this CH3 now is attached to coupled to one proton. So, you expect a doublet, and that is a doublet here, and finally, this lone CH is now coupled to 2 and 3 5 plus 1 6, that is what we saw here, and that is a sextet. So, this is basically coming from here. Now, because it is attached to an aromatic ring is also causes de-shielding, remember we saw that, and because of the de-shielding, that hydrogen is coming around 3 ppm. Regularly it should come around between 1 to 2 or 2.5, but normally it is coming little bit downfield shifted because of this aromatic ring. So, this is how this structure matches with the given spectrum. Okay. So, let us look at another example where again we have an aromatic spin system, aromatic group. How did we figure out there is an aromatic group? Is basically based on again the bunch of peaks appearing around 7 ppm. Okay. So, here you see there is a bunch of peaks, and we do not go into detail analysis here, but what we will see is basically count the number relative protons. So, there are 5 protons, 2, 2 and 3. So, if you add them up, it attaches to about 12 protons, and 12 protons is what we get here, we expect. But now there is an oxygen group here, earlier that was not there, and that probably is causing this downfield shift of this. Okay. So, what basically is happening is that there is a CH2 because there is a 2 now, this is not a methyl. So, there is a isolated CH2 which is attached to an oxygen. Okay. That is what is interesting, that there is an isolated group, and what is this particular case here, you see a triplet and a quadret. So, what could be happening is that now again if you analyze this data, we have seen this coming many times, that whenever you have this kind of a thing where you have a triplet and a quadret, so it could be again something like this, that there is a CH2, CH, and this is basically giving me a triplet, and this is giving me a quadret. But if that is so, then I should not have anything here, no hydrogens should be present here. If there is a hydrogen present here, that will give rise to another splitting, but that is not the case. So, that means there is no hydrogen there. So, what could be, and then we have on here we have a phenyl ring. So, we have a phenyl ring here, and there is a singlet which is coming basically because of a methylene group, because a methylene group only can have 2 peaks. You cannot expect a methyl group to have 2 peaks, and therefore, so let us see how we can put it together. It basically is something like this. So, here we can see that there is single oxygen, and because there is no direct oxygen attached, this particular peak is not downfield shifted. So, this is what is shown here. So, this is this 2, it is an isolated CH2, isolated because The nearest hydrogen to this for coupling is this side is here and this side is here, the ortho protons, and all of them are 5 bonds away. This is 5 bond away and this is more than around 5 or 6 bond. So, therefore, we do not expect any coupling. So, this is an isolated CH2 methylene group, and that is what is showing a singlet, and it is downfield shifted. It is coming around 3.7, 3.8 because it is attached to a CO on one side, which is not very strongly electronegative like a direct oxygen, but definitely a more electron withdrawing because of this oxygen here, and also the electron withdrawing or a de-shielding factor coming because of the benzene ring. So, both of these together make this proton become downfield shifted. On this side, this is what we saw, there is a CH2 and a CH3, and that is what standard. Remember I said that it, whenever you see a triplet methyl and a quartet somewhere in 2 ppm, automatically it means this is the group present, but this group is not attached to oxygen. That means it has to be attached to something else, but if it is attached to a hydrogen, I mean carbon containing a hydrogen, then you will not expect quartet, because this hydrogen, if there was present, that hydrogen would add to this. So, 3 plus 1 4 plus, so you would expect a quintet for this. So, when if you are getting a quartet for this, which means that there is no hydrogen coupled to this hydrogen on this side. So, that is only possible if there is a group like this, and if it is not an oxygen, it is a carbonyl group, because a ketone group, because that will not downfield shift this so much. So, it comes around 2.5 ppm. So, based on this consideration, carbonyl group, we can say that this CH2 is attached to a CO, I mean because based on the chemical shift, and this side is basically this. So, this is a molecule which we can see. Now, one thing is, if we had again a carbon spectrum with us, we would have actually looked at the carbonyl peak in the NMR spectrum, and that actually gives you a very nice peak at around, depending on the functional group, around 180 to 200 ppm, 170 to 200. So, there is a wide range of distribution, and depending on whether it is an ester group or it is a ketone group, or it is a carboxylate group, or it is a aldehyde, and so on. Based on that, the carbonyl frequency is very specific, and that we can use. So, this kind of brings us to the end of this class, and we have looked at basically 10 examples of how we can analyze proton spectrum given only the composition and not the structure, how we can get reduce the structure. But remember, this is just the way exercise for you to understand how we can use the spectrum, but we do not in reality, in practical, in real research, we just do not rely on proton spectrum. We also use carbon 1D spectrum, we use IR spectrum, we use mass spectrum, and so on. All these together are used. Remember, why do we need mass spectrum? Mass spectrum is useful because we can get the information about the unsaturation, degree of unsaturation. There is this famous rule of 13, which is used to deduce the index of hydrogen deficiency, or basically getting the unsaturation. So, that is useful. Then you know whether there is a ethylene bond. Remember, we are not looked at any pi bond analysis currently in this proton spectrum. We will take up the pi bond cases when we come to the carbon experiment, and so now what we will do in the next class, we will start with carbon 13 NMR, where we will look at 1D carbon 13 NMR. Again, we will go through the same process as we did for proton, looking at what are the factors which affect the chemical shifts, what are the coupling patterns, and so on. Once we understand how a carbon spectrum is recorded and what kind of data we expect, we can then combine with proton NMR again to look at some more examples of how to solve structures given only carbon and proton NMR, and then we will go on to 2D NMR.